Guys, before we learn our last gas law formula, the ideal gas law, we need to talk about moles of a gas. Now, a couple chapters ago, we learned about our friend Avogadro, and we learned about his number, 6.02 times 10 to the 23rd. And in our class, we call that our new favorite number. Now, this is an extremely large number, and it can only be applied to extremely minute particles, such as atoms or molecules or formula units. A lot of textbooks call 6.02 times 10 to the 23rd the chemist's dozen. Like you can say, I have a dozen eggs and I have 12 eggs. I have a dozen cars and I have 12 cars. I have a dozen pencils and then I have a dozen diamonds, maybe not. And I have a dozen dresses or a dozen shoes. A dozen can apply to lots of things because 12 is not a very big number. But a mole, 6.02 times 10 to the 23rd is 1 mole. Even though technically you could apply it to a lot of things, it would be illogical. For example, if I said I want to have 1 mole of oranges, well, guess how much volume 1 mole of oranges would take up? It would fill the earth. If we could open the earth up and dump a mole of oranges in there, it would fill the earth up. So it's illogical to say I have a mole of oranges because the earth can't sustain that. I can't have a mole of trees. I can't really even have a mole of paper. But I can have a mole of atoms, molecules, or formula units because those things are so tiny, it works for us to apply the mole to them and it actually makes our calculations easier. But what about a mole of a gas? Avogadro stated that 1 mole of a gas have equal volumes at the same temperature and pressure. 1 mole of a gas will have equal volumes at the same temperature and pressure. It doesn't matter what gas you have. Well, how is that possible? Because we know, according to the periodic table, that molecules all have different sizes. What if I had a hydrogen molecule and I had an oxygen molecule? Now, according to the periodic table, a hydrogen molecule weighs approximately 1 mole of hydrogen molecules weigh approximately 2.0 grams, and 1 mole of oxygen molecules weigh approximately 32.0 grams. So an oxygen molecule is much bigger than a hydrogen molecule. So how can Avogadro say, and how could his hypothesis state that equal volumes of gases contain equal numbers of particles? Because of one thing. Remember, in the kinetic theory, we said that gases are extremely far apart. So if these hydrogen molecules are inside this container, and let's say this container has a volume of 22.4 liters, that's just some number I came up with, this would be 1 mole of hydrogen. But if I had this box is also 22.4 liters, and if I had it filled with oxygen molecules, even though, isn't it funny when you try to be random, you land up making a pattern, even though those molecules are larger, they're still so far apart from each other that their size doesn't matter relative to the great distances between them. The size does not matter relative to the great distances between them. So, how could Avogadro come up with our hypothesis? It's because whether the particles are large or small, there's such a lot of space between them that their size does not matter. At STP, and last video I taught you that STP stands for standard, temperature, and pressure. Avogadro hypothesized that 1 mole of a gas takes up 22.4 liters. So it doesn't matter if it's 1 mole of hydrogen or if it's 1 mole of oxygen. 1 mole of a gas, their size is not important because the spaces between them are so far apart. 1 mole of a gas takes up 22.4 liters at STP. So how big is 22.4 liters? Okay, I've tried to come up with some pictures. If this box here represents 22.4 liters, a basketball would be approximately this size relative to that box, a soccer ball approximately this size, and there's a 2-liter bottle. Well, wait a second. Well, I can just do the math. 22.4 liters divided by 2 liters. If I wanted to go and pour this in here, 11 2-liter bottles would take up 22 liters. So that would mean there would just be a 0.4 liters space left. So our new definition and our new conversion factor is that 1 mole of a gas, of any gas, at STP occupies 22.4 liters. So it gives us our new conversion factor. 1 mole is equivalent to 22.4 liters, or 22.4 liters is equivalent to 1 mole. And we can do all kinds of good math with this. So for example, if I said to you, what volume will 6 moles of oxygen gas, 6 moles of oxygen gas, occupy at STP? What volume? You would just put down your given, put down where you're going, volume in liters, and now you write your conversion factor. Which one are we going to use? Well, we have moles here, so we need moles down here. And 1 mole of any gas has 22.4 liters. So I use this conversion factor right here. Remember, you always want to do these so your units cancel and you're left with what you want. So now all I'm going to do is I'm going to say 6 times 22.4. We're going to ignore sig figs for now, and we're going to get 134.4 liters of oxygen gas. Now, sometimes your teachers may use a grid like this, or sometimes they may write their conversions like this. It's the same thing. I use a grid because I'm so sloppy and it keeps all my stuff together. But whether you use this method or this method, it's the same thing. It's dimensional analysis. It helps with any conversion and it makes me very happy. What if you were given a volume and told to find moles? For example, if I told you I have 19.5 liters of, let's do hydrogen gas now. How many moles? How many moles do I have? Or how many moles is 19.5 liters of hydrogen gas? Well, we can use dimensional analysis because we've been doing this all year. 19.5 liters of hydrogen gas. And I want to go to moles of hydrogen gas. Now I know it's a gas, so therefore I can use one of these two conversion factors. Which one am I going to use? Well, I'm going to use the one whichever allows my units to cancel so that I'm left with what I want. So right here I have liters. So I'm going to put liters down here. And then I'm headed to moles. Whoops. So I'm going to put moles right here. And then I need my number. What is the conversion factor? There are 22.4 liters. Now, how did I know to place liters on the bottom? Well, all I'm doing is I'm placing my units so that they cancel and I can be left with what I want. All right, so now I'm going to say 19.5 divided by 22.4, and I'm going to get 0.87 moles of hydrogen gas. So what have we learned today? We can convert easily between moles of a gas and volume of a gas. We've learned that it doesn't matter what type of gas you have, it's always going to have the same conversion factor. And the person we have to thank for all this knowledge is our good friend Avogadro, who gave us the mole. And all his research started with gases. Remember, this holds true at STP, standard temperature and pressure. So you know where we're heading next. We're going to learn how to do this at non-standard temperature and pressure conditions, because in Florida, we're never sitting at 273 Kelvin, which is 0 degrees Celsius.